Okay, so now we're going to look at the von Neumann stability analysis in order to explain why in our previous video where we started coding out our equation for thermal diffusivity, why that if our R value ended up being greater than 1/2, our values would skyrocket and kind of blow out of proportion. And that just it's just a kind of an issue with the way our equation's set up, that it skyrockets so much. But let's look at why R cannot be greater and how it fails within our equation. So again, I'm going to draw a bar. I'm going to try 10 sections this time. All right, it's 10 sections. 0 to 9. And so, again, we can look at, right, so we have our change in time change in time and change in position, right? So now if we look at our change in, not our change in time, our time as n being the number of intervals and delta t, our change in time, being the interval, right? So if we're looking at intervals of every half second or every second, right, that's delta t, so it's going to be 0.5 or 1 or 0.25, however large or small you want your interval to be. And then the number of intervals we're looking at is n. So, and that multiplied obviously gives you the time. And then our change of position is going to be similar, except we're going to use j as number of intervals of position, and delta x is the length of the interval that we're looking at. And so by doing this, we're going to be having our temperature values with respect to our j and our n, the number of intervals that we're looking at. And so we can then replace our if we go back to our original temperature equation, now we can look at it in terms of our n and j. We can change our our t and our x value. We can plug in for our t and our x. So we have our e to the negative alpha k squared, and instead of t, we can put in n delta t, and then e to the, remember, the I k x or j delta x. So now from here we are able to so if we have this, we're able to then look at our the equation that we got in video 2 that we just coded with, right? So if we do n and j, we can look at n plus 1, right? So if we're solving for our following temperature in the following section here, we do n plus 1, and that is equal to t jn, right, the previous value, and that is plus our r, which is what we're looking at. Remember, r is what we're using the von Neumann stability analysis to prove that or to show why r cannot be greater than 1/2. And so we have our r multiplied by t j plus 1 n minus 2 t j n plus t j minus 1 n. And then we can simplify this further by factoring out a t j n, right? So if we transfer this down, t n j, and then well, we can factor out a t and j from this equation here, and so we'll have r t j n, and then in order to kind of simplify this further, we're going to look at our Euler's again, or Euler's, which we remember as e to the I k delta x is equal to cosine x plus sine x. And by rearranging this and kind of plugging in for the IKs, we can basically replace this with cosine x. So if we then continue it down here and plug it in, we can, so in order to do that, we can look at our t j plus 1 n as a result of this, right? We can look at all of this. Again, we're taking out a t j n from this term. So we're basically just looking at the one after and the one before, as well as the one in the center here. So get e to the I k delta x, and then minus, we have a 2 here, plus e to the negative I k delta x. And again, what we're looking at here is the value ahead of, our temperature value one space in advance and one space in behind. And so, right, so then the negative kind of transfers up here. And now we can use our substitution for cosine. So, and I'm also going to combine these two TJNs here, just to kind of separate. Again, we're eventually working down to separate this R out. And so we have our T n plus 1 J is equal to T n J and then 1 plus R and then it's going to be from up here, this value 2 cosine k delta x and 2 cosine k delta x and then minus 2. So essentially these two together gives us this term, and then we subtract our 2 still. And now further we can pull out another 2 and basically just kind of focused on this term here. Sorry, let me clear some space up actually, because I might need just a little bit more space. So if we look at that term that we just derived with the cosines in it, and separate out the 2, we'll get 1 plus 2r, and then everything on the inside, the cosine k delta x minus 1, and then essentially our R value has to be less than 1, and then simply by kind of looking at this equation here, simplifying it down, right? So we get the 1, so it turns to a 0. We've got the plus 1 over here, and then divide by 2. Our R value we then get has to be less than 1/2. And this is basically the proof that our R value has to be less than 1/2, or else this term right here that I brought down will kind of skyrocket. It'll grow exponentially, and we won't be able to get good values out of our code with that one.